Well, welcome back. Here's a very beautiful problem that has a lot of things involved in it. So let's see what it's all about. You have a mass of, or a disk of a mass of 5 kilograms as pictured with a diameter of 60 centimeters. Okay, meaning that the radius is going to be 0.3 of a meter. And it shows in a figure that it rotates on the axle passing through one edge, as shown in the picture. So what I'm going to do here is actually draw a line. Maybe I draw another picture that will be maybe better. Zoom in a little more. So the axle is parallel to the floor. So this is the axle. It's parallel to the floor. And the cylinder is held with a center of mass at the same height as the axle and then released. So essentially when you release it, this is going to just kind of drop like so. And they ask you what is the cylinder or the disk's initial angular acceleration. And then the cylinder, so angular acceleration, that will be alpha. This is in radians per second square. And what is the cylinder's angular velocity when it is directly below the axle? So when it gets all the way perpendicular right here, at this point, when that reaches this point, what will be the angular velocity omega? Omega at the bottom, I guess. And that will be in radians per second. Well, let's see how we would approach this problem. So first off, I'm going to attempt to make another sequence of the picture here. So assuming that, and this is kind of moving, huh? So assuming that this is dropping down, I'm going to change colors here and attempt to make another circle into the new position. All right, so that's not so good, I guess. Let's try that again. Now let's make it, oh, that's good enough, I guess. I'm going to erase that part. So this is my new position that we need to look at. So the center moves to the center right there. And the edge moves to the edge. Let's put it with a different color so we can see it better, what we're looking at, right? So position number 1 and position number 2. And when this happens, you essentially have this omega also happening. And I guess then there's this omega here going this way, omega at the bottom. So let's make sure we understand what are we looking at actually. So we're looking at the omega below, right? When the position drops. All right, so let's kind of go through and ask ourselves, how would we do this? Since you have the axle parallel to the floor, and this rotation doesn't happen to the center of mass, you will always have to recall the parallel axis theorem. So first of all, the center of mass should be as the same height as the axle and then released. So this is your center of mass right at this point. And then release, so it goes at 90-degree angle right below the axle. All right, so let's kind of look at this. So what happens? You have gravitational potential energy, right, that transforms completely into kinetic energy of rotation, or rotational kinetic energy. This is what happens in this problem, essentially. So having said that, you have to consider in part A, in order to find what is alpha, well, alpha is part of the torque, because you have a torque happening here, right? So you have your angular acceleration alpha times the moment of inertia. And which inertia are we talking about? So it's the inertia in compared to the edge, or yeah, I guess it's okay to call it like that. And then you have to look at this. At the edge of the disk, you have the I caused by the center of mass of the whole disk or cylinder plus m times d squared, because the whole diameter matters here when the top point 1 here becomes 2, right? Goes from 1 to 2, something like that. So now we have the center of mass here is, or it's a disk, so we have 1/2 mass r squared. Boy, I'm getting tired, plus m. And our distance this time, if you really look at it, is times r squared. Okay, so it is essentially the moment of inertia about the disk's edge is obtained by using the parallel axis theorem. So we've done that in a lecture, and that's kind of like the illustration of the parallel axis theorem. Since we have this parallelism with the floor, here's a plane, right, of the floor. Okay, so with that being said, this becomes 3/2 mr squared. We have everything we need about that. So 3/2, the mass is 5 kilograms. And then the radius is 0.3, right? Because the diameter was so, okay, so 0.3. And these are meters and all squared. So if you use your calculators for that, you get 0.675. And those are kilograms meter squared. Okay, so now that we have the moment of inertia about the disk's edge, okay, so this is about the disk's edge. Why? Because it's going right, the rotation happens about that edge right there. So one edge moves from top to bottom, right at the 90 degrees. Okay, so now we have to think about the torque. So let's kind of depict the torque for a moment. So if we find each one of them, and then we plug back in, we're going to be able to find that alpha. So what is torque? Well, that's RF sine of theta. So if you look at our picture, we don't have anything else, but the only force that we have here is the force of the weight of the disk or the cylinder. So this is nothing else but mg. All right, so we have R mg sine of, let's talk about, remember what I said, this is your 90 degrees move, moving down by 90 degrees. Okay, so our radius right here, 0.3. The mass is 5 times 9.8, or 9.81 sine of 90. Okay, which is nothing else but 1, right? So this is 1. And I just want to be kosher about all of them. So let's see, what do we get? If you plug everything in, you get 14.7. Those are Newton meter. Okay, so well, now we have the torque, and we also have the moment of inertia. Marrying them all together, we get that alpha is nothing else but torque over I. So all right, so that would become 14.7 divided by 0.675. And I am getting, I didn't finish this one, so let me do that. 21.777, so 21.8, and those are radians per second squared. All right. So here it is. We answered the first part of the question. What is the angular acceleration? Alpha, we just found it, 21.8 radians per second squared. And now the second question, or part B, is what is the disk or the cylinder's angular velocity when it's directly below the axle? So they don't ask you the Yes, you cannot use the rotational kinematics in it here, but we have to use conservation of energy. So let's see what energy we're talking about. If you look at the situation here, the conservation of energy tells you that the total energy final must be equal to total energy initial. Final, you're looking at kinetic energy final plus potential energy final equals kinetic energy. And this, when I talk about kinetic here, we talk about rotational kinetic. Okay, initial plus potential energy initial. So I'm going to depict each one of them. So this is a disk, hence the kinetic energy of rotation is 1/2 I omega squared. So since it is final, I call it at point 2, I guess. So I'm going to call it omega 2 plus potential energy final. Well, potential energy final, it will be 0, right? Because you release the disk and it goes down and it kind of stops right there. And if you consider the floor or the height as a reference, this is the height where the potential energy is 0. Yeah, so at the very bottom, you get the potential energy is 0. Equals, if you look what happens to the disk, the kinetic energy of rotation initial, that's kind of released from rest, meaning that you have a 0 as a kinetic energy, okay? And then plus the potential energy initial, well, that will be the height. So the height is nothing else from phase 1 to phase 2 is 2 times the radius or simply the diameter. So, but if you are considering angular velocity as directed below the axle, then it will be the angular velocity of the center of the mass. And I think this is the ambiguity of this problem, right? So it should be the same omega. So I'm just going to consider that height of the radius. So here's your 0, I guess, for potential energy. And here's 0 for the kinetic energy. Okay, so going back here, I'm going to have that equals to mgh, right? So in our case, it's going to be mgr. And the reason we have to go by the radius is because in the formula for the moment of inertia and the omega, the radius is involved. So you kind of have to stick together with the same kind of constants in there. So let's see what do we get. Let's plug in what we have. So 1/2 I omega 2 squared equals to mgr. Multiply with 2 and divide by I. Multiply with 2, divide by I, and then you square root that. All right. So we get the omega 2 equals square root of 2 mgr divided by I. Now go ahead and plug in your numbers. What do we have? 2, the mass was 5 kilograms, 9.8 or 9.81, radius 0.3, and I forgot how much was it, 0.675. When all said and done, we get that omega is about 6.5 something, 56. 6.59, I'm sorry, so about 6.6. And those are radians per second. So hence we found what we were asked to find. See you later.